How are you, everybody? Just forget about the inconvenience caused by the MCO. Just embark your rigorous revision program for your SPM examination. Right, today we are going to continue another new topic on electricity, and I can foresee this is a more difficult one. Electromotive force and internal resistance. So in this lesson, you must know how to define electromotive force, or in short form we call EMF, gain an understanding of internal resistance, and learn to use the equation, and also to sketch two important graphs. So we begin now. What is EMF? Definitely EMF is not a force, even though it is named as electromotive force, but it is not a force. So you can never put down EMF in Newton. So what is EMF? It's almost similar to voltage. When you talk about voltage, you spend electrical energy. When you talk about EMF, you produce, you generate, or you make electrical energy available. See the difference? Spending money and earning money, they are different. But they are both measured in ringgit, Malaysia. So the EMF of a battery or a cell, a battery and a cell, they are not the same. A battery is an assortment of cells. It can be 5 or 6 cells joined up to form a battery, right? That's the difference. So it tells you how much electrical energy produced or generated by the battery when 1 coulomb of electric charge is driven by the battery around a complete circuit. So the formula E is equals to W over Q, where W is the electrical energy generated in joule, and Q is the charge driven in coulomb. And therefore the SI unit, if you follow the equation strictly, it should be joule per coulomb. But nobody will write down joule per coulomb. They prefer the abbreviation, we call it the short form, VOLT, symbolized by the V, capital letter V, okay? Capital letter V. Okay, now how are you going to measure EMF of a battery? So the method is very simple. You put your voltmeter across the terminals of the battery, but make sure that the switch must be open. Why? Because when the switch is open, there will be no current. So I put down the current will be 0. So if the current is 0, you'll find that the battery is cold because there is no current flowing. In other words, there will be no loss in electrical energy. So you'll find that the voltage that you measure, and since you connect it across the battery, we call it the terminal voltage, will give you the full voltage supplied by the battery. So the key word here is the full voltage. And this voltage, you call it the EMF. So whenever the battery is not delivering any current, then the voltage that you measure is the maximum voltage. And that is called the EMF. Okay. Now, what if you close the switch and see what happens? But by the way, the voltmeter reading, as you know, is the EMF, okay? Okay, now, you close the switch. Once you close the switch, you expect current flowing, okay? And once the current flows, you can see that the lamp lights up. And also the battery is no longer cold, yeah? It's hot. That's why when you turn on your torchlight, you try to touch the battery after 2 or 3 minutes. It's hot. Yeah? It's hot. So, when heat is produced inside the battery, that means the battery has to use up some electrical energy for the charge to pass through the battery. So it looks like battery itself has resistance. Battery itself has resistance. So that's the reason why you expect some voltage loss. Okay? And the resistance found inside the battery is given a beautiful name. What's the name? It is called the internal resistance. Yes. So it's just like you don't just find enemy within your friends, also could be outside your friend circle, inside and outside. So in this case, when you close the switch, the voltmeter reading will be lesser than the EMF. And EMF is the total voltage that can be supplied by the battery, should be equals to the voltage to where? To the external circuit. And in our diagram, it's a very simple one. Your external circuit refers to the lamp. But from the principle of conservation of energy, you have to account for the voltage loss memory. So it will be the voltage loss in the battery. So the one you give to the external circuit plus the one loss should be equals to the total voltage that can be supplied by the battery. And the name given to it is called EMF. So mathematically, EMF should be the big V plus the small v. The small v refers to the voltage loss. You got me? And the voltage loss, you can always use current times the R, and the small little r stands for the internal resistance. So voltage to the external circuit is the I times the big R. Big R is the resistance of the external circuit. So in our context here, it refers to the resistance of the lamp. Got it? Resistance of the lamp. Therefore, when you combine both, it will be equals to the big V equals to the I big R, and the small v equal to I small r. So when you combine, it will become this one. Yeah, you substitute inside, you expand it, you factorize it, you will come to this equation. So therefore, I can actually write down 3 important equations for you all, yeah, which you need to remember. Number 1, you need to know that V is always equals to IR. The V refers to the voltage to the external circuit. Secondly, you must know E is equals to the V plus the I, small r, yeah? And finally, is the E equals to IR plus the R. So I will show you how to make full use of these three equations in the question that I'm going to show you later. You follow me? To get this, as I said, you just substitute this into here and substitute this into here. Then you factorize, you will come to this. Simple mathematics, okay? Okay, lastly, we have to talk about the graphs, important graphs. So to plot graphs, you have to design an experiment. So the terminal voltage is the one across the battery. It doesn't give the EMF unless you cut off the circuit. Understand? So the V represented here shows the voltage given to the R. So we put ammeter in series with the circuit in order to measure the current. And we have a rheostat. It's a variable resistor. It's for us to change or to vary both the voltage and the current. Okay, as you know, E is equal to V plus IR. So we encountered this, don't know for how many times already. You rearrange, you will get V as a subject equals to minus IR plus the E. Okay? But you rearrange, put down V equals to minus RI plus the E. You just change. Why? Because the I is a variable and V is a variable, whereas R is fixed. Internal resistance is fixed. This one is called the manipulated variable, and this is a responding variable. So you look at this equation, it's very, very similar to this straight line equation right now. Y equal to mx plus c, where y is v and your x is actually I. Looks like it's a straight line equation, but the gradient is not a positive gradient. It's a negative gradient. So I expect you to get a graph this way. But remember, your intercept C is E, right? So therefore the intercept will give you the E, and the gradient will be minus R. So in this case, the V-intercept is the EMF, and the gradient is the minus R. And remember, the shape of the graph is such, the gradient is always negative. So negative with a negative R, you're going to cancel out, so your R will be positive. Okay? Now look at another graph. From E equal to I bracket R plus R, you can rearrange the equation to write it this way. And then you bring the small r to the other side, you will form another equation here, where the R is the resistance of the rheostat. It's a responding variable, and you see this as your manipulated variable. Okay, so what type of graph you're going to get here? What type of graph? It's also similar to y equals to mx plus c, right now. But you can see your y-intercept is a negative r. So you have to put it here. And the gradient is positive. Oh. So from here, the r-intercept is a minus r, but your gradient, m, is actually the EMF. Okay, so in terms of theory, this is end of it. But physics, you need a lot of practice, okay? So let me see some simple questions to make you to understand the thing better. Okay, look at this one. Look at these questions. How are you going to solve this kind of questions? If you read the question carefully, a voltmeter connected directly across the battery gives a reading of 1.5. And you can see the switch is open, right? So straight away you know your EMF is 1.5 volt. And therefore you already answered this part. Settle. All right? So jot down whatever information given in the question. The voltmeter reading will go down to 1.35 when you turn on the switch. And the current recorded is 0.3. And you're asked to find the internal resistance. So how are you going to do it? Not the external, the internal. So my suggestion is you can always try out this equation. And look, your EMF is 1.5. Okay, the voltage to the external circuit when the battery delivers current is 1.35. And current is given as 0.3. So simple mathematical manipulation will bring you to this answer, 0.5. Okay, so this is the first example. Now you look at another example, number 2. A circuit contains a cell of EMF 3 volt. 3 volt, you see? So EMF is 3.0 volt. And internal resistance is an unknown. But you know external resistance is 10 ohm. And the potential difference across the external resistance is 2.5. So what is the question? Find the value of the current, I, as well as the internal resistance. Okay, so to find the current, you can always use V equals to IR. Correct? So voltage is 2.5. Current is an unknown, but your R is 10. So obviously, your I will be 0.25 ampere. After that, you use E equals to I, R plus R. At the beginning, you cannot use this equation because you don't know the big R. So you understand that, right? Sorry, you don't know the small r. So you cannot use this equation. But now you know the I, then the story is different. So this is 3, 0.25. The big R is 10, is given. And the small little r is an unknown. So a little bit of arithmetic will bring you to the answer, 2 ohm. Is that easy? Yes, it's very, very easy. You may say at the beginning, why don't I use this equation? Because you don't know the I, you also don't know the R. So even though the equation is a correct equation, but it's not suitable, okay? All right, look at the next example. A circuit consists of a cell of EMF 2. Volt, okay? EMF 2 volt. So you write down EMF 2 volt. So they ask you, what's the voltmeter reading in open circuit? Open circuit means you are measuring EMF. So straight away you can put down 2 volt here. It's very simple, am I right? And now what other information given? The internal resistance is 0.5 ohm. And the current flowing is 0.4 ampere. And you are asked for the external resistance. So you see here, the voltmeter is connected across the terminal of the cell. So to solve this, I suggest you can just use this simple equation. Because all the information required are there. 2, 0.4, and the big R, you're looking for that. So your R should be equals to, I think it should be 4.5 ohm. Okay, so to get the voltmeter reading, you just need IR. So what's the I, my friend? 0.4. What's the R? 4.5. So that will be 1.8. But alternatively, you can also use this to get your answer. It will be exactly the same. EMF 2, current 0.4, internal resistance 0.5, and that will give you 1.8. Clear? Very good. Okay, look at the next example. So it's a graph of V versus the I. The V versus the I. And what did I say? They ask you for electromotive force. Just now we already learned in theory, electromotive force is given by the V intercept and here. So straight away, you know it has to be 6 volt. Whereas internal resistance is minus R is equals to the gradient. So 6 minus 2 will be 4 divided by 2. This is 0. But don't forget, the slope itself is a negative gradient, right? Yes, just like what I say. So that means your R is positive in value. So it's a 2.0 ohm. It's clear? Okay. Then you look at the last example. It's the R versus the R versus the 1 over I graph. And I said before, in case you've forgotten, sorry, your E is equal to this. So your R plus the R will give you E times 1 over I. So your R will be E times 1 over I minus the R. So to find the internal resistance, you just need this, which is the intercept. So your minus R is a minus 0.2. So your R is 0.2. The EMF is a gradient. A gradient, you need a triangle. So if you measure from here to here, it's 1.3. But from here to here, there's no value given. So how do you do it? You extend the graph to make it a bit bigger. So you can make use of this triangle. So vertically, this one should be 1.5, and horizontally 0.5. So your EMF is equals to the gradient. Yeah? So it should be 1.5 divided by 0.5 to give you 3.0 volt. Is that clear? Okay, very good. So from the 5 examples that I've given you, please go back and refer again the examples, and believe it will consolidate on your understanding on this topic, electromotive force and internal resistance. Bye. Thank you.